Physics is confusing, so let's do our best to try to understand. What we're looking at today for modern physics is fission and fusion curves, which are kind of the same thing, and a little bit about stability. Um, Within the kind of turn of the century, 1800s to 1900s, one of the issues that was coming up in the world of astronomy was actually how do stars stay bright? How do they continue to give off light? Because at this point in time, we knew that if we wanted to give off light, we had a few methods to do it. We could burn wood. You could make a campfire. Um, but if you worked out the calculation of, how massive is our sun, and how long would some mass of wood of that size actually burn, the sun burns out very quickly. So you need to find better things than wood to create a sun with. So you try things like oils. You can have an oil lamp, and the sun is still burning out too quickly. It's burning out, for wood maybe like hundreds of years to thousands of years. For oil, maybe thousands of years. Even if you use like one of the best things at the turn of the century, like coal to burn, you're still burning out the sun in hundreds to thousands of years. And this is rather unfortunate because around this time as well, we had begun to discover nuclear particles, and we had started to understand that due to radioactive decay and some dating that we did with that, that the Earth was not only hundreds or thousands or tens of thousands of years old. We began to learn that the Earth was billions of years old. So we need something that can burn in the sky for billions of years. And we didn't really have anything that could do that. It wasn't until we started to really understand some nuclear physics, really looking down into what's going on with our particles in and of themselves, that we began to understand how stars are actually giving off light for these immensely long periods of times, allowing us to have a nice night sky filled with the stars from eons ago. And one of the methods of this is the idea of fusion and its counterpart, fission. When you have fusion, what is actually happening is you are taking two elements and you are bringing them together, and they are fusing together, hence the idea, fusion. You're bringing their nuclides together. And whenever you do this, you are creating a heavier element, very similar to Goku and Vegeta, paching, becoming something new. When you bring these two things together, they are fusing and becoming something new. So if you take hydrogen and fuse it together in a star, you actually get all sorts of like weird isotopes of things in terms of like helium-2, 3 and whatnot. But you're essentially fusing hydrogens into heliums. These heliums go to oxygens and carbons and lithiums. Like, you go up the periodic table in terms of mass. You begin to fuse things together. Now, if you notice here, because of the binding energy, which is that missing mass that we had previously, if we look at the binding energy per nucleon here, what actually happens when you fuse things together is that the binding energy per nucleon changes. And what actually occurs is whenever you get a nice transition from going from hydrogen to this fancy helium and then up to here to actual helium-2, 4, you release all of this excess binding energy. You get that out. And this is very nice because for stars, gravity wants to collapse them into nothingness. But if I'm releasing this binding energy, I'm pushing back against gravity. And it's allowing the stars to continue this fusion process, because this fusion process takes some energy to put into it in order to get this to occur. So stars are burning up hydrogen here into heliums and heavier elements, and it's this difference in binding energy that is allowing the stars to push back against gravity and maintain their life. Now, this first jump here is the best jump a star is ever going to get in terms of efficiency of burning stuff, and that's why hydrogen's such a nice thing to burn for stars. If you have more and more massive stars, they can continue to burn out heavier and heavier elements. But as we notice on this curve, as we kind of go up here, this curve really curves out here. It kind of like plateaus at some point. And looking at this curve, and I want to burn oxygen, I'm getting some energy out of it, but it's not a terrible amount. These differences here are very small. So while large hypermassive stars can burn these heavier and heavier elements, they're not getting the same return on their investment as they did when they were burning hydrogen and helium. However, even the most massive stars reach a breaking point. We call this breaking point right here. This is the iron peak. It turns out that you can fuse elements into iron, and in doing so, going up that ladder, you will release some amount of energy. It's like it's a net gain for you to do that for the star. However, when you reach this iron peak right here, you now start to travel the other direction, which means that, in theory, you can fuse heavier elements together. Like, we could keep going up in this direction, but it actually doesn't help our star. It actually costs our star energy to fuse heavier and heavier elements. So the star just won't. The only way we can get heavier elements like this is through a supernova explosion where the star is in its death throes and we just get tons of energy shedded out. And when that energy is just shedded, it's able to do some last fusion for everything that's heavier than iron. So that's one of the interesting things about stars and supernova explosions. Now, on the other hand, while fusion is bringing things together, we also have this idea of fission. And this is what we actually use in our nuclear reactors. Because with fission, instead of bringing things together, we will let things separate or break apart. And in doing so, we move back up the curve. But when we move back up the curve like this, it's a similar idea to what was happening before with our hydrogen and helium. By moving backwards on this curve, we are getting differences in energies here. And these differences in energies for each of these decays allow us to, in our reactor plants, harvest that energy and do useful work with it. The most common way we do this in a reactor plant is you take water, you heat it up into steam, and then you pump that steam through a turbine, which is pretty much how all reactors work to some extent, or all energy plants work to some extent. Photovoltaics or solar being, obvious exception, and geothermal being exception as well to an extent. But we're just harnessing this difference in energy on this fission curve. So if we're going up in the curve, we're getting heavier and heavier masses to the iron peak. We have fusion, and technically we can go further with fusion. It's just we'll only see it if we would like to lose energy out of the equation. But if we're always wanting to gain energy here, we can go backwards past iron with a fission and, obtain some net energy given off as a result. Okay, so this is a really very helpful curve. And the iron peak here is the top. It is the king. Now, in terms of some of the forces that are kind of binding nucleons together and whatnot, there is a force that is really holding these nucleus together. What we have here is the strong force. And the strong force holding a nucleus together, it is really a short-range force. And technically, there's also a weak nuclear force here. Both of them are short-range forces. And what we mean by a short-range force is that they are only taking place on the order of like 10 to the minus 15 meters. So they are like really short range. They're only really working within the nucleus of themselves. And this is because for our strong force, these are actually governed by gluons, which are located in quarks in and of themselves. So it makes sense that only the proton and neutron have this force associated with them. But it is interesting that this force is a short-range force, that it's happening only on the inside. Because on a counterexample, there are some long-range forces out here. Gravity and electromagnetism. These are long-range forces. They're governed by 1 over r squared laws, so they go out infinitely forever. For a short-range force, once you get past this 10 to the minus 15 meters, it's done. You're not going to feel it, which is kind of an interesting thing, in comparison to these long-range, which extend forever. So this strong and weak nuclear force, they only seem to function within the nucleus of themselves. The strong force is keeping everything together. This weak force is a little interesting. Essentially, the weak force pops up because there are times when you should have a stable nucleus that should not undergo a spontaneous fission, but it does so anyways. So we call this weak force, I like to call it at least, it's the push off the cliff, because that fission shouldn't really occur, but the weak force is like, boop, and it makes it occur anyways. So that's the general idea of the weak force there. Now, if we kind of take a look at this graph once again, we should see that our x-axis here is the number of nucleons, or the mass number. And if you recall, this is both protons and neutrons here. And this is rather important because this proton plus neutron number, we call that atomic mass number, which is Z. And, or excuse me, we call this the atomic mass number A. Ugh. However, if we just look at our atomic number, if we just look at the protons, Z, then we see a very interesting trend. As the atomic number, the number of protons here, goes up, in general, so do the number of neutrons. And if we took a look at helium was 2, 4. For each proton, we had a neutron. Lithium is 3, 6. Carbon in general is 6, 12. You're almost just like doubling up, or you have the same number of neutrons as protons in all of these scenarios. This is generally true. Generally speaking, the number of protons will equal your number of protons. This is only true, though, until your atomic mass is somewhere around 30 to 40. Things get weird. There's all sorts of stuff with like copper and different shells and like things going on. But around 30 to 40 for your total atomic mass number, that's like Z15-ish to Z20-ish. Generally, this is true. Once you hit this point and you get a little bit after this, what you start to see is the number of neutrons in a nucleus will actually start to be larger than the number of protons. And if we go up here and take a look at this out here, this last point, this is uranium here. It's not really the last point, but it's the last point given here because we use uranium in a lot of fission reactors. Uranium has 92 protons, but its total atomic mass number is 238, which means there are much, much more neutrons than there are protons here. So generally speaking, once you get past 30 to 40 as the atomic mass number, a Z of about 15, then you start getting more neutrons than you do protons. And the reason being is that our nucleus is becoming so big that we are starting to get some instabilities with electrostatic forces, and we need a larger, strong force to hold them in. Because if you imagine you've got a bunch of positive charged particles here, all these particles want to push away from each other. And for the other matter, there's a bunch of electrons out here they're attracted to. But if we just put a bunch of neutral things in here, bloop, 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 and that strong force is very large, saying, whoa, 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 you're staying, then we'll overrule that simply because we have more and more neutrons there. So this is a very helpful thing. Generally speaking as well, we are going to have generally stable nucleuses up until Z equals 82. So up until about 82 protons, we are going to be stable. Once we get beyond 82 protons, and we've got these larger and larger objects, we start to become non-stable or unstable here. And what we mean by stable is it will stay together like indefinitely. Like it could stay together forever to the end of time and not have an issue. Once you get beyond this, you start to get into some radioactive decay states, and things start to go a little bit south. And if you know anything about what is this element at Z equals 82, this is lead, Pb. Lead is where all of our radioactive isotopes, things like uranium and things around that item, whenever they start to decay, whenever they start to fission, and we'll talk about this in greater detail, they traditionally fission down until they hit lead. Once they hit lead, everything's kind of over, and we get a nice stable element once again that's not going to undergo spontaneous radioactive decay. So a very, very cool thing there. So just a little bit of footnotes on some of the atomic mass numbers we see, some of the atomic numbers we see, why we see some trends on our periodic table, and why, as we're going to see, lead is a nice stable element versus all these very, very heavy things up here for our fission curves. Okay? So with that, this is finished. Until next time, adios, and take it easy.